Good morning. My name is Amber Burt, and I'm an architectural technologist and BIM manager at P3A. I've been with P3A since 2011, and I've been really pushing the use of BIM and Revit in the office since my first day. With the help of a select few, I've worked extensively on developing our internal Revit and BIM standards. For the College Avenue campus project, I operated mostly on the periphery of the project, jumping in to help problem solve or help troubleshoot an issue, modeling issues as they arose. Towards the end, I was brought in to help with the development of the interiors portion of the construction documents.
Hi, I'm Kate Jackson. I'm now a full architect. It's changed in the last 2 weeks, so that's exciting news for me. I worked on the College Avenue project from 2016 to its completion in 2018. I assisted in design and contract administration, and I worked closely with the Technologist that developed the Revit model that was used to generate our construction drawings for the project.
In our office, within the last 5 years, we've gone from about 20% of our projects being done in Revit to about 90%. The benefits we see have been astronomical in accelerating our workflow. Some key benefits include in visualizations that become developed early with the design process, and therefore allowing the client to be involved in the development of the project to a greater extent. Coordination has gone to literally another dimension. Some of the growing pains we face, much like other firms, is adoption. Adoption both internally and external consultants and owners has been a challenge. One area of struggle is how to bring the design process into our Revit workflow. The interface of Revit often gets in the way of our designer's workflow. It is fairly rigid, and Kate will speak more to this later. P3A's first project in Revit was done very much as a glorified CAD project. No Revit protocols or standards were established, and at the time, people didn't like that the drawings produced didn't look like P3A drawings. But when I came along, so now we have some established Revit protocols, and we have regular coordination meetings with our consultants to review clashes within models and coordination. I think that with each project we get better, and that it's because our office fosters a very collaborative atmosphere. At each project, we sit down as a team to do a post-mortem, and we talk about what worked, what didn't, and what maybe didn't work on this project but could work on another if X, Y, Z was followed. So the imagery on this slide shows our progression from our first Revit project on the bottom left to a project we did in Swift Current, Riverview Village Estates, and then the SRFC Rough Riders boardroom on the right, and finally to Darke Hall in the Connexus head office building.
As an introduction to the project, the College Avenue campus project involved extensive renovation and rehabilitation of a complex of heritage buildings, and it included 2 additions. The first phase, which has been completed, includes the complex of buildings that you see on the left side of the screen. And we're currently working on the Darke Hall project, which is the building on the right-hand side of the screen. It's a theater that was completed in 1929 that is currently being restored. The project has been an enormous effort of a very large team. You can see all of the consultants we have listed here on the screen, and our team included a heritage consultant, an acoustics and theater consultant, as well as structural, mechanical, and electrical, as well as envelope expertise. From our small office, nearly 80% of our staff have at one point or another worked on this project. But let's quickly go back to why it's so important, why this building is so important to the city of Regina. The construction of the main building was completed in 1912. And this was the first building in the complex. It was designed by Brown and Valance from Montreal. The building began its tenure as a Methodist high school. So that's the entire complex. You can see to the left of the tower, that was the first block that was built in 1912. In 1916, a local architect, J.H. Punton, completed an addition that added the girls' dormitory building, or those of you from Regina, we know it as the conservatory building. That's to the right of the tower. And at this time, the tower was also completed which was originally planned by Brown and Valance but was executed with the construction in 1916. In 1925, the school became associated with the University of Saskatchewan and began offering some programs to students there. Eventually, it became the Regina-based satellite of the University of Saskatchewan. In 1953, a gallery building was added, which was also the birthplace of another local institution, the Mackenzie Art Gallery. By 1974, the University of Regina formally distinguished itself from the University of Saskatchewan. And in 1967, the building of a new suburban campus had begun. Over time, the university's degree-granting programs moved to the new campus. College Avenue campus became the home of many non-degree, community-oriented programs, such as music studies for the general public, career advancement programs, and lifelong learning programs for seniors. These buildings have been a part of the local community for over 100 years, and they've been a formative part of many lives past and present.
In 2015, under direction of the University of Regina, P3A began documenting the building to begin restoration project. That would require a significant funding source to be completed.
By 2015, the buildings had fallen into disrepair. Most significantly, the foundations of 3 of the buildings had been compromised by Regina's highly volatile clay soil. In the image on the left, you can see how much the building is moving by how much daylight you can see on the right side of that window jamb. And on the left, you can see some of the cracking that we found behind the face brick of the conservatory building. The University of Regina was seeking to rehabilitate these buildings, but additional funding sources would be required to get the project done. So while the scope of the project was to be determined, P3A performed as-builts to generate a base set of drawings.
At the beginning of the project, very little drawing information was available as the original drawings had been lost to time. The process for generating as-builts was both a very high-tech and a very low traditional effort. The exterior envelope of each of the buildings in the complex were meticulously mapped using a technology called point clouding. This technology was used because getting accurate measurements of the building, in hard-to-access places such as stonework on the 3rd story would be very difficult and time-consuming to do using traditional methods. It would likely be a painstaking process utilizing a lift that would allow someone access to measure each detail by hand. So instead, we hired a company to scan the building using a 3D scanning tool called a ferrofocus laser scanner and generate a point cloud. The point cloud is a series of points in geometric space. Each pixel has a coordinate location. So you can see in this image that it looks pixelated and fuzzy because as each dot is a scanned point. Once the buildings were scanned, we brought the point cloud model into Autodesk Recap. We quickly realized that it was going to be too slow and would be too arduous to work with in its entirety. So instead, the technologist broke the recap model into smaller segments to bring directly into Revit to measure off of. On the left are measurements of a window that have been done in recap. The entire model was very accurate to within plus or minus 2 millimeters. So elements like the intricate stonework window surrounds could be replicated with incredible accuracy. On the right, the blue elements in the background are the point cloud imported into Revit. In front, in the white, is a superimposed Revit family of a rounded bay window. This was modeled based on measurements obtained from the point scan. As I mentioned, working with the point cloud had its challenges. With 14.4 billion points recorded for the project, the model was very heavy and very accurate. The model had to do a lot of heavy lifting. In order to work with the point cloud, we had to break it apart. The accuracy level proved a challenge when it came to modeling the building, as it showed in great detail 100 years of building movement. The building had settled by a foot on the east side, which made the point cloud model difficult to use in some places. It didn't really make sense for us to model our building slanted, so our as-built model needed to account for the difference, which meant we still had to go back to site to measure things and piece the puzzle together. All masonry units were individually tagged, modeled, and reviewed to note down the condition of the stone. If required to be replaced, it was drafted individually and sent to our masonry subcontractor in order to recreate the masonry element. Here you can see a partial snippet of the stone tagging done in elevation. Similarly, other key heritage elements were documented and scheduled, such as doors and windows throughout the project. Much of this was done with pen and paper on site. The elements in the model were tagged and scheduled manually, and the as-built schedules were not brought into Revit. The accuracy of the model was vital to restoration processes as well as for adaptive reuse. In this instance, an entire vestibule was documented. Each stone was modeled, tagged, and individually scheduled with remarks on its condition. On site, each stone was removed, tagged, and stored before being reconstructed in a new location later in the project. And here is that stonework, reconstructed in the west entrance of the west addition. Here is an example of a window surround. On the left is a salvaged window. In some cases, only damaged stones were refabricated as infills. On the right, you can see the restored window surround. Some original stone is still making up of the coining on the sides, but the head and jamb had been refabricated. Most of the interior as-builts were done by on-site measuring. This was more efficient than point cloud scans of the interior. First reason being that measurement of the spaces was easy to do as these were all smaller spaces. Secondly, the point scanner would have had to have been set up in each room within the campus, and there are hundreds of rooms. With the time constraints, this was just not feasible. Therefore, key heritage spaces were point clouded to provide us with high fidelity source to reference. Heritage details were sketched and measured by hand. A tool called a contour gauge was used to measure and document trim profiles throughout the project. When the gauge is pushed into a profile, the pins register the shape. The shape can then be traced onto a sheet of paper. That sheet of paper is then scanned, brought into Revit as an underlay and traced over to create a profile. The profile is then used within the model. This is an unusual amount of detail, but we felt it was necessary for the heritage record. The profile was also exported and provided to our mill workers to fabricate new trim when salvage trim was not available. And this is an example of some of that completed millwork that has been restored. So between the point cloud for the exterior and the interior as-builts, we were able to determine dimensions and thicknesses of walls, but everything in between remained a mystery. Making assumptions was not an option, as every detail was critical for heritage conservation. Selective demolition was required to investigate and determine existing conditions such as wall construction, beam and floor connections, floor assemblies, and the foundation was also excavated and exposed.
Selective demolition gave us an understanding of how the building was constructed in theory, but in practice, construction methods could vary room by room. Some of this variation may date back to the building's original construction, but some of it is due to the fact that it's 100 years old and many renovations have taken place. This unpredictable existing condition meant that we were frequently required on site to address conditions that were unknown before they were exposed.
Here's the final model complex of the existing building as it looked back when design began in 2016. It took 2 experienced technologists 2 months to complete.
In the spring of 2016, the University of Regina received federal funding for the project. The project could not start until the funding was acquired, and the funding came with the stipulation that the project be substantially complete by the fall of 2018. This meant that the team had 27 months to get from the beginning of design to substantial completion. In a traditional project, we fully complete a phase of design before we move on to the next one. We move from loose illustrative sketches and schematic design to design development, and only after the completion of construction drawings does construction begin. In a fast-track project, these phases begin to overlap. It becomes a challenging process where, in this case, the structure of the building was issued for construction before we knew where the interior walls would go. So to give you a visual representation of what that looked like, this is what our model, what the design model looked like in the beginning of 2016, and this is the completed building by the fall of 2018. Fully utilizing BIM for design was a challenge on this project. BIM involves building a model that is precise, centralized, hosts one version of the truth, whereas design thinking is in the beginning, iterative, and not fully defined. These two drawings illustrate the difference between these two processes. BIM is precise, organized, and complex. The design sketch on the right is loose and illustrative. While both of these describe the same location within the project, they are very different methods of working. This is a process that, in my opinion, hasn't fully found its home in BIM. Design is fluid and multiplicitous. It's often in a state of it could be this or it could be that. But in a fast-track process like this is quite an uncomfortable state. We were completing the foundation package to be issued at the same time as we were developing these concepts for the exterior envelope. Revit tools are restrictive when designers are trying to work in the state. I personally find with Revit, you have to have a good idea of what your output is supposed to be before the start, and early design doesn't work like that. So the design team worked in SketchUp, in Rhino, on paper, built models, sculpted foam, and finally whittled our design into a form worthy of Revit. The model was then completely rebuilt by the Technologist in Revit due to the difficulties with coordination between these softwares at the time. But of course, the carefully crafted as-built model was useful in this process. It was stripped down and jammed into other programs to experiment with. It was sliced into plans and sections and pulled into AutoCAD to examine different possibilities. And without such a holistic starting point, the design wouldn't be what it is. We studied the geometry of the existing heritage facade from the model, studied spatial relationships, studied floor level discrepancies, and much more. This pattern of pulling elements out of the model and into different software and experimenting with them and then revising the model occurred throughout the design process. Above is an example of an illustration where the model was pulled into SketchUp, substantially revised. The image was generated and we had a conversation with the client. Once the client had approved the direction, the model was then revised to reflect the changes that we had made. Having a detailed model also assisted us in quickly visualizing our concepts, and this can help us to bring the client on board with our design direction. One standout example was for me the porte cochere. A porte cochere, you can see the example of on the far left. It's an open portal that leads through a building to an academic quad beyond. In the case of College Ave, the arch intended for the porte cochere at the base of the tower had never been utilized. In fact, the lower half of it was the mechanical room for the campus. A floor level bisected the arch. Early on in the design, the image in the middle of the screen was created to make the argument for using it as the new entry to the campus. In a very short time, we were able to communicate our vision of being able to see through the building to the other side. The comprehensive quality of BIM models allows us as designers to generate visuals which assist clients in understanding the project. This allows them to participate in much more thoroughly in the design process. This is a 360 stereoscopic rendering of our Heritage Lecture Theatre on campus. I'm excited for where design visualization will go in the future, and I'm excited for when it will be common to place clients in a VR experience early on in the project.
A phased Revit model was used to generate all the documentation for the project, from demolition drawings to project completion. The complex was made up of 6 architectural models and 3 models from sub-consultants. The size of the overall architectural model was 1 gig. One model was used for existing parts of the complex, and another was used for the renovated parts and additions. Another model was also created for the conservatory facade. This image shows the extent of demolition that took place in preparation for construction. It also shows the support towers that supported the conservatory facade while the addition was built behind it. And finally, this shows the completed design with the east and west additions in place. More than 60 drawing packages were issued to enable the fast-track construction of the project. Here is an example of the different packages issued for one location in the project. This is the existing conservatory building that was demolished due to the significant damage that had occurred to the structure. The retained facade is on the top of the drawing. The foundation package was issued first before the design of the facade and interior layout had been completed. The envelope of the building was issued next, before interior design had been fully completed. And then the interior package. And then finally, a floor finish package. So you can see that at least 4 architectural packages made up this section of the building alone, but it was required to facilitate the fast-track project.
This 3D view shows how we were using Revit during the construction documentation for coordination with our sub-consultants. You can see ducts, beams, conduit tray, and piping. College Avenue campus has very sensitive spaces that were not designed to conceal modern utilities. We worked with our consultants to provide services to these spaces without impacting the historic qualities of the space. Being able to solve these problems three-dimensionally and in collaboration with our sub-consultants is critical to the success of these highly technical projects. This involves a greater engagement in BIM processes from every member of the design team. The more information we can provide in the model, the more problems we can solve prior to construction. You can see in a complex space such as this, 2-dimensional drawings are insufficient to communicate and examine the problems at hand. The issue is that for this project to meet the deadlines required, all of these systems had to be designed at once. So this kind of conflict was ultimately inevitable. But luckily we had the model to assist us with resolution. One success of the project was the coordination of services through the Heritage Corridor. In the college building, we wanted to maintain the original ceiling heights in the corridor, which meant that there was no ceiling space to run services in. We worked with our consultants to ensure air distribution systems did not cross the corridor and that sprinkler lines, electrical, and data distribution only crossed at the corridor 4 times and in line with existing beams. So that's what you can see on the left-hand side. In the middle of the drawing where there's sort of clear empty space, that's the corridor, and then the 2 darker lines running through it, that's where we're running all of our services crossing the corridor.
Not everything could be shown in a 2D graphic and be communicated clearly. Here we see a few isometric details that were provided to the contractor to communicate some tricky details. On the left is a 3D drawing provided by the structural consultant to help describe how directional piling was to be performed and how the structure was tied into the facade to be retained. You can see that there's much more data communicated in the 3D drawing than in the traditional elevation.
Likes to flip slides. Contract administration was a very large part of our involvement on this project. This was for 2 major reasons. The first being that the heritage buildings are complex and there's a lot of unknowns that came up during construction. For example, beams not being where we expected them to be. The second reason was the speed of construction. The contractor was beginning work before all of the drawing packages had been designed. The contractor is not aware of what we may be planning, and so we have to assist on identifying issues that may be impacted by upcoming packages. Finally, the complexity of the project, the detailing that was required was extensive, and nothing could be identified as typical, as there were variations required in every room of the project due to the as-built condition. P3A performed a daily walkthrough on site with the contractor, and the top 10 issues were identified and addressed by instruction later that day. And I think the model really helped in our understanding, our holistic understanding of the project, which helped us to solve these problems. Having a spatial understanding of the relationships in 3 dimensions assisted what directions we could give on site. This is an example of some of the markups that were provided by instruction every day. As you can see that Kaylin, the technologist that led contract administration, got very good at drawing 3D shapes in Bluebeam. The pace of this project meant that we couldn't detail every connection, bulkhead, etc. that would pop up. Some of them could not be anticipated beforehand. Physically, we couldn't model everything because it would take too long to get the information communicated to the contractor. And we were fortunate to have a working relationship where these details could be described and drawn by hand when the issues arose. This is what had to happen to meet schedule, and is a very low-tech solution, but it was facilitated by our Revit model with a combination of photos, from the site as well as views from Revit. So you can see on this slide, we're mostly looking at photographs from site that are then traced over. And in this slide, you can see that we're using the Revit model to illustrate what's going on. This was useful for clarifying items that might otherwise require multiple views to explain. For example, the markup on the right was about how to frame in a gypsum board wall on the backside of the retained conservatory facade. This would have required multiple sections as well as an elevation to describe. BIM continued to be a useful tool for us as we moved into contract administration. In this project, we were not using a contract administration software that integrated with our model on site. Our presence on site was fairly traditional, a notebook and a camera. But our three-dimensional understanding of the project can be attributed to the scope of the model we were working in day to day. And we could use that model to problem solve issues that would not be possible without it. When there are questions that arose on site about how to route water lines, ducts, conduit, we could go back and cut multiple new 3D isometrics through our model and assist with the resolution of that routing issue. It also helped me to visualize the potential aesthetic impact of any of the decisions that we were making during the construction administration process.
Ooh. So some lessons learned. More planning and mapping out of our model structure at the beginning would have benefited us. 2 models, one for existing and demo, and another model for new, proved to be cumbersome, and having them linked further proved to be a challenge. New template management between design and construction. We had templates created for designers, but if they weren't managed, it did cause some issues with our construction documentation. This was more of an experience issue. Point cloud, as I mentioned before, it's difficult to work with for generating models, and it requires separation into smaller elements in order to work with it. And it was a little too accurate at times. However, it was good as a double check. Work sets, because we did exterior and interior package work sets, work sets were an easy way to toggle phases within the model. We could use the same views with a modification of visible work sets. And then for the multiple drawing packages, Revit assisted us with sheet numbering. The team sat down and mapped out a numbering scheme for all phases and projects and packages. The multiple drawings were necessary for a fast track project, and it causes more work for drawing management and more time required for coordination and potential for confusion on site if the newest package was not distributed. And finally, manage those models. As there were at least 8 people working on the model at any given time, model management was crucial. Cleaning up the warnings, which were often attributed to people just ignoring them, as well as the general complexity of the models. If the models were not managed, they got slow, heavy, and could cause delay to the design and the production teams. There were a lot of lessons learned that we've been able to implement and improve our current projects and processes. And overall, this was a large project for our office, and with so many people having touched it and worked on it, it really brought up the skill level and understanding of Revit and BIM within our office, and also proved its usefulness. I look forward to the next one.
So we didn't have time to go through the final result of what happened with this building today. And so we have a few views of the finished project to cycle through to finish off our presentation. This is the exterior, so that's the new addition and the original building. These are some interior shots of renovated classroom space, renovated boardroom space in the middle of the building. The corridors, which were restored to a heritage condition, the drop ceilings were fully removed. This is the new entry sequence. This is the tower. An entire atrium was added to the south side of the tower. And that's another view of the atrium. Thank you very much.